a second. I'll come back to you then, okay? So, how about Abby? Okay, who else also has a high melting point? Ionic, right? So those are two characters that are similar. Erin, tell me something about metallic bonding. Okay, so that's sea of moving electrons. Do we have a picture for that on our little chart? Did you try to just describe that through a oral representation? Made it hard. That one I actually have a picture up here for you, okay? So keep yours at your desk for a second. I want to make sure that we're clear on the properties, and then we're moving on to actually why things bond and how to draw these bonds in a little bit of a different kind of perspective. So before we move on, let's get a Kahoot in, okay? Kahoot, pull out your phones, go to kahoot.com, and we're going to log on to Kahoot so we can actually do this quick properties quiz. You have your sheet in front of you, you have the little table, the blue stuff in front of you, and let's jump on this. So Kahoot it, and then let me pause music so it can play its own music. Here is the game pin. Okay, there. Okay. 851529. Yeah. Get on computer. Yeah. Go ahead. All right. So put some names in there. I can figure out who you are. Like again, do not put like Bootylicious. I don't know who it is. And then I know you want to. All right, 16. Can I get a couple more? Okay. Yes. Okay, I'll write the games on the board if you get kicked out or I'm not in. We're starting in just a second. Yeah. Yeah, if you guys can see it from computer, that is. All right. Let's do this. This is use your notes and stuff, okay? This will be our quick review here. All right, properties of chemical bonds. Here we go. I love Kahoot music. Which bond happens between an S metal and a non-metal? And I have free will to move on once I get most of my people. Do I have everybody? Almost? Okay, ionic. So it's basically asking about metals versus non-metals. Ooh. Okay, S block means metals. Non-metals are on the other side. So we're clear blue and green. Transition is a metal, but not S block. Okay, yeah, Paige. Okay, keep going. Metals are always song they have. Okay, I'm going in 5 seconds. Okay, I gave you too much time. Good. Metals. Oh, okay. I can see why you picked that. Okay, metals always form cations. We're clear on that though in terms of ionic bonding. Metals always form cations, meaning they always lose their electrons. Yeah, they're also shiny. Okay, we're moving on. Yep, moving on. Which types of bonds share electrons? Nice. Keep it rolling. Last one. Okay. Whew. Come easy. Okay, so far so good. One person, people. Whoever that is, Shane, you have one job. Okay, look at your notes. Which type of bond is the strongest, causing the highest melting points? This is how multiple should always go. Like 30 seconds or less. Shouldn't hurt. All right, 26 and 27. 27. good. Strongest bonds mean high electrostatic attraction. Very, very good. I don't have any zero found. Which type of bond is between two or more nonmetals? So I can ask these things in many different ways, right? All right. Nice. Okay. So covalent share between two nonmetals. Keep going. Why in the heck do elements bond? You may have investigated this. All of these. Okay, to become more stable, there's only one reason. Elements want to become stable just like we do. They bond for that reason. They'll achieve octet through their valence shell, and there's usually some attraction going on, and that minimizes their overall energy, which makes them happier. We'll go into that into more depth, so that was all of them. How can electrons participate in bonding process between elements? How can electrons participate in bonding? Good. Okay, all these. Yes. Okay, you see the theme here. Okay, so they can really do anything. It depends on the type of bond. Why is an ion, or what is an ion called that loses an electron? I get a couple more. Nice. Okay. Lose an electron. Losing an electron makes you overall more positive cation. Are we good on that? We're just being like brain fartish. Stop brain farting. No more. Okay. What is an ion called that gains an electron? Oh, I wonder what this one is. So I'll be using these terms a lot. I'm going to make sure you're good. Clear? Yes. Great. So the losing or gaining an electron means you have an additional negative charge. You're an anion. Which of these ionic formulas is written correctly with the cation first? So think about who forms cation. Okay, that's a pretty good spread. This is a hard one because first of all, you look for something that was going to form an ionic, which was a metal, non-metal, magnesium, and chlorine. You can look at your periodic table for that. And then the metal is written first because they form cations. A little bit more involved, right? But are we clear why this is ionic? Yeah? Okay. Which of these is a covalent compound? If you need your PCOE, have it out. You'll need it a lot today. Okay, how would one figure this out? Right, you look at the nonmetals. Covalents are between two nonmetals. The only one that has two nonmetals is sulfur and oxygen. This has got a calcium and a potassium and iron in it. Those are all metals. Those are out. Okay. Ooh, inload. Who's inload? It's not me. I'm not participating. Okay. Which type of bond usually results in gases and liquids at room temperature? All right. Okay, that's a good spread. So we have covalent, property of covalent compounds. Good. Which one is only electrically conductive when in molten or aqueous states? Very good. Let's see. Oh gosh, what in the world? So molten. So the word "only" is the part that throws you off. The metallic bonds are always electrically conductive. It doesn't matter if they're solid, liquid, or in aqueous. Well, they're not going to change in aqueous. They don't dissolve. Metals do not dissolve in water. That would be an awful occurrence. Because every time you wash your hands, your jewelry would fall off. Every time you take a shower, your earrings would fall out. Every time you put water in a pot, the pot would dissolve. That'd be awful. We could never hold water except for plastic and glass. That's it. Okay, so metals are always conductive. Always. Only the time that ionic things are conducted, electrically conducted, is when they're molten or aqueous. Which ones are soluble in water? Another word for water is aqueous solution. And I just went through that, so. Okay, good. Metallic does not dissolve in water. We just went through that. You want me to do it again? Every time you wash your hands, your rings will fall off. Every time you put water in a pot, it will dissolve. Metallic things are not dissolving in water. Okay. Which has delocalized electrons, creating properties of malleability and ductility. Okay. I knew this would be the hard one. What is this asking for, really? Which ones have metallic bonding, right? Identify, what kind of bonding is this? Covalent, it's non-metal, non-metal. What kind of bonding is this one? Ionic, that's metal, non-metal. What does that have to be? Metallic, because it's just a metal. A metal bonding with itself is metallic bonding. Okay, so that one gives properties of metallic bonds. Next, which one's a sea of electrons giving properties of electrical and thermal conductivity? Okay, again, what was it simply asking for? Right, a metallic bonding situation. This one's metal, non-metal, non-metal. This one's metal, non-metal. This is metal. So it's metallic bonding. I think we got one more. Oh, no. I don't know who this is, but I will find out. Okay, so we have, oh, nope. Yeah, Maddie, Lindsay, Paige, Allison. These are extra credit. And your rainbows. Okay, so. Lovely. After you, let me just get a quick screenshot of this so I don't forget who I just said was going to get extra credit. Okay. All right, guys. Let's move on then. So let's put some notes, okay? We have bonding properties. I feel like your cartoon will really let you know, or your story or whatever it is, that you know what the heck you are talking about when we talk about molecules and their bonding types. So we're going to take a couple notes. The metallic bonding situation, I told you I was going to need to get a picture for it. It's best described by something like this. So I'm going to scroll back up so you can see this right here. Look at these pictures. Do you see a cation and an anion? Do you actually see an anion in these pictures? An anion would be if an atom gained an electron. What do you see? You see a cation, and then what else? Just a bunch of electrons. Well, the only thing that's happened here is this cation has lost its electron, but it's hanging around, it's still close. So we call this a sea of delocalized electrons, meaning a sea of electrons that move around. They're very mobile. They are delocalized because they can move to different locations. So if you want a quick picture of of a metallic bonding situation, give yourself a quick sketch. It's just a cation core with some electrons around it. No anions inside it. There's literally no nonmetals. And so, if you think about it, what are these little guys, these little electrons, what are they going to be able to do really freely? Move, okay. What kind of properties might that give that you know metallic bonding has? Electrons can move. Say again. Think of the properties of metallic bonds. Alina, what you got? Malleable, right. Malleable, what does malleable mean? You can what? Flatten into a sheet, right. So basically, if you want to take this and flatten it into a sheet, what happens is when you start to flatten it, the metals and the cations and the electrons move to fill the gaps and to spread out. Because they're mobile, they can do that. What other properties? Ductile, the same thing. You pull them into a wire, the electrons and the metals fill the spaces of where you're trying to pull it, right? Okay, what else? Right, why in the world would these loose electrons be able to conduct electricity? What is electricity? The big question of the day. What's electricity? It's just the flow of electrons. That's it. That's all electricity is, okay? Electricity is the flow of electrons. So every time you use electricity, electrons are just moving from point A to point B. So if they are free to go, like they're free in this little mobile state, and you want them to flow in one direction, they do. Okay? What cannot do that? What doesn't have free electrons just to move around? Ionic bonds or covalent bonds. So they're not going to be like a solid ionic structure like this. This is not an ionic structure. This is a model of one. It is not going to have any electrons that are free to move. Okay? These electrons are stuck on the cation or stuck on the anion. They're not going to move unless you put them in water or in molten states. So that's interesting because that's electricity flowing and thermal energy flowing through the metal cores as well. So there's the little blurb there for you on metallic bonding. In my verbiage, right, if you want to add this to your notes list where you took down some properties of the metallic bonding, this is kind of how I phrase it, and you'll see me phrasing it more often. Interparticle attraction, not a bond. Interparticle attraction. And that's kind of what sets a true bond. Okay, so after this, we're going to jump into log. Okay, so as they lose their electrons can move around, which gives them the properties. So everything you should be kind of associating is the structure of the bond, like how it forms, and the property that it attains. So that's why we kind of have that list that helps you organize it. And I'll keep referencing these quite often. But metallic bonds, we're actually going to hopefully make a metallic bond by creating an alloy. What's an alloy again? A mixture of two metals. And we'll make it a mixture by heating it up to high temperatures, and then we'll actually test it. Not today, but later. Okay, so we don't have a picture for that. The other ones I think are pretty self-explanatory. So let's talk about why bonding happens. So the red stuff and the highlighted stuff is usually the most important. So if you don't write anything else, write that for me. This is basically what we talked about on the Kahoot. Why does bonding actually occur? Like, it obviously has to help these elements out. If not, they wouldn't do it. They're not doing it just for kicks and giggles. They're doing it because they actually want to get down to a lower energy state where they're nice and stable and happy. So as you can see, hydrogen, I did not mean to do that, okay. Hydrogen here on that ion and hydrogen on the other atom, they have a positive core, meaning their nucleus, and the other one has a positive core, which is nucleus. The nucleus on hydrogen A is really, really liking. This is nucleus A in the middle. It is really liking these electrons that are out here for our hydrogen. Same side, same story, other side. The nucleus from this atom is really liking meaning attracting, right? The electron out here in the outer cloud of hydrogen. So that's the attractive component. So when that happens, they actually get together and they form that bond. But if they get too close together, the two nuclei will overlap, right? And this is not going to happen very nicely because the two of the same charges, they do not attract each other. The rule is opposites attract. Likes repel. So they can't get too close. They're just going to get close enough for them to bond so that the attractive nature of it is really energy stabilizing, meaning that opposites attract, creating a lower potential energy. So the potential energy lowers, and that's like more of an advanced concept. But that's really why these things are bonding. There is a purpose. They both benefit. It's a win-win mutualistic activity for them. So whenever that occurs, generally they're going to get octets. right? 8 valence electrons. And it's going to happen either by transferring electrons or sharing electrons. That's the only way you're going to get octet. So if that happens by transferring electrons, then we've now created an ionic bond. If that has happened through the sharing electrons, then we've now created a covalent bond. That bonding happens because they want to get to a stable state and they want to get to octet. Give me a thumbs up whenever you're good to go here. So pull out your periodic table as you're waiting for me, okay? And then maybe one that you don't mind labeling and writing some stuff on. Not your next blank one, but it can be a previous one that you've colored on or so I want you guys to label okay, so mine's a little ugly, let's just be honest. But I want you to tell me how many valence electrons are in each of the groups. How many valence electrons are in group 1? 1. How do you know that? What does it end in the electron configuration? So blank S1, right? So if you're ending in S1, you have 1 valence electron, so 1 VE. Guess what group 2 has? 2, because what does it end in? So blank S2, right? So 2 valence electrons. You skip these, so this is group 1A over here, group 2A. Group 3A, where aluminum is, where does it end? Say again? Where does it end in its electron configuration? Oh, wait. P1. It ends in P1, right? But what came before it? S2. So it was like, let's go for our boron, for example. It was 2S2, 2P1, right? So the second energy level has how many valence electrons? 2 from the S block and 1 from the P block. So it has 3 valence electrons. So group 3A has 3 valence electrons. Group 4A, take a guess, guys. 4 valence electrons. How do you know that from the electron configuration? Right, 2s2, 2p2, right? 2 plus 2 is 4. So keep going. 5a has 5 valence electrons, 6a, 6 valence electrons, all the way over. 6a is 6 valence electrons, 7a is 7 valence electrons, and 8a has 8 valence electrons. And that's the 8 that we desire, right? So where does their electron configuration end for like, example, neon? 2s2, 2p6, so 2 and 6 is 8. So that's how we get there. So everything we've done previously is really important here. So you're going to see that we're going to be referencing the valence electrons the entire day today in this entire unit. So if you remember the group number is the valence number, we are awesome, we are good. Okay, so on your property table, only write down these additional highlighted ones because we're going to get into bonding here in a second. But the one part of the ionic bonding that was not on the website, it mentioned it in a couple of the websites, but I didn't ask you to write it. You could write it on other properties, for example, is the strength of it depends on the lattice energy. The strength of it, and maybe if you just write on the back of the table, that's fine, whatever you gotta do, depends on the lattice energy. I'll explain to you what this means in a second. We already talked about the electrolytic part, so we're good. So lattice energy, this is a lattice, right? You drew a structure of a bunch of cations and anions alternating between each other. This is a lattice structure. It looks like, I don't know if you know what a lattice is on like the side of a house. It's kind of repeating nature, okay? So let's do an example of that. Somebody pick out a metal from group 1 or group 2. Pick out a metal from group 1 or group 2. Okay, magnesium. If magnesium has 2 valence electrons, what is its charge going to be when it forms an ion? Plus 2, right? If you have 2 valence electrons, you're going to lose those 2 valence electrons, and that makes you an overall 2 plus charge. Okay, so we've chosen a metal. Choose a non-metal from group 4 and over. Sulfur, great. So sulfur. Sulfur's ending in 2s2, 2p what? 4. Okay, how many more? Does it want to gain or lose electrons? Gain, how many? 2. So if you gain 2 electrons, what's your charge? 2 negative. Okay, so the way we figure out the lattice energy is the strength of something called the charge product. Charge product means 2 really easy things. These are the charges. What does product mean in math? Multiply. Okay, guys, multiply those charges. And then take the absolute value. So 2 plus and a 2 minus equals absolute value 4. Okay, so a 4 charge product is what magnesium sulfide has when it gets together. Let's compare that to something like potassium chloride. Okay, what's potassium's charge? Look at its valence electrons. Tell me if it gains or loses. Loses, so what's its charge? +1, right. Look at chlorine. So it's 1 away from noble gas electron configuration, so it gains 1, -1. So charge product for this would be a -1 times a +1 equal 1. Okay, who has a greater charge product? Right, the magnesium sulfide example. So who is the stronger ionic bond? Magnesium sulfide. So when I say you can compare the lattice energy, the strength of the bond, you look at their charges and you multiply them. If you have to say who's got the stronger bond, you just have to look at the periodic table and look at their loss working electrons. So this one's a stronger ionic bond because of its charge product. Okay, so that's how you compare the strengths of ions. Covalents don't have charges. They don't make ions. They don't make, the loss working electrons. So they don't have this. We will only do this for ionic. Okay? Okay, so for covalent, the other factoid you need to record is something called volatility. So right here, volatile. Anybody see that in the reading from the websites? Volatile. Okay, so volatile. Raise your hand if you put deodorant on this morning. Everybody raise their hand, guys. There's only one answer here. Okay, so you put deodorant on. Why? Oh. Okay, so you don't smell. So instead of smelling you and it's not you guys that smell. You realize it's just your bacteria. So only blame your BO on bacteria. It's not you. They're just acting a fool. They're acting up and they are really reproducing in there. They are basically emitting gases that make you smell like that. Okay, so it's not you. But to cover up the scent of your bacteria, you put on deodorant. Well, deodorant is just like a waxy kind of oily feeling thing, right? Do you think that's more ionic or covalent? Say again? Covalent, right? Butter, oil, things like that. Those are nonpolar covalents, okay? Deodorant is a covalent compound with lots of other stuff in it too. But it is volatile, meaning has a very good likelihood of evaporating or vaporizing or making turn into from a solid to a gas, okay? If it can vaporize easily, that's what volatile means, by the way. Vaporize easily. It releases an odor. So guess what, guys? Your hot body is making it just do its little thing and evaporate and make you smell good. 98 degrees or so is really going to make things melt or evaporate very easily. So that's how perfume works. You spray perfume on you. The perfume itself is not making you smell good until it starts to vaporize off your body. Your stuff in your hair, like in terms of shampoo and conditioner, they have a scent to them. It's usually as really lightly or really high vaporizability covalent structure that's in the shampoo or conditioner. Anything that vaporizes easily is called volatile, which is really good for us to smell good. It's also really bad for things we don't want to vaporize, like what? Let's say I had a cup of water here. I came back. Do I want it there? Yeah, I do. I don't want it to vaporize because then I would never have a chance to drink it. So water actually has a very low vaporizability, even though it is a covalent compound, and that's something we're going to get to a lot later. Okay, so I'm going to ignore that last part there. All right, we did that. Oh, this is a lattice structure. Yay. Okay, moving on. This is just a repeating nature of ions and a covalent, or ionic, cation, anion, cation, anion. Okay, tell me what you see here. Tell me what you're observing. What do you notice? Okay, so you're noticing valence electrons. How are we depicting them? As dots. Okay, and then you'll notice that, for example, helium, despite the fact that it's in the noble gases group 8, how many valence electrons does it have? 2. Okay, this is called the duet rule, not the octet rule. meaning helium is just so little, it can't get octet. It's just that small. Everything else gets octet, though, in that group A. So what we're going to start to do is actually depict these valence electrons as dots. We're going to show them how they bond. And these are called Lewis dot particles. Guess who came up with this? This guy named Lewis. Okay. Told you. You got names after yourself if you ever become big shot. All right, so let's do ionic first, and then we'll move on from ionic and go to covalent. I'm going to turn the lights back on. This is an yellow box for it's so bright. You just have to deal with it. Specifically, you need to draw this down here. If you don't draw anything else, draw that. Okay, so what we're showing here is that sodium single valence electron, and it's described as one dot here, right? We can see that it's being transferred to chlorine's 1 valence or 7 valence electrons to allow sodium to backtrack to its previous octet state and for chlorine to gain octet state. The way you show that at the end is by showing the yield symbol, the positive nature, so the cation that has formed from sodium's loss of an electron, and then the anion formed when chlorine gains an electron. So we are literally showing the transfer nature of the ionic bond. And so what happens whenever these two things get together? What happens when a positive one is added to a negative one? What does it equal? It says, what did you say? Okay, so they're attracted. That's one thing. Their electrostatics attract each other. And it's neutral because a +1 plus a -1 is equal to 0. Every single ionic compound, when they get together, is called electrically neutral. Electrically neutral. I guarantee you this is the multiple choice question people will forget. This is the multiple choice question. Something about electrically neutral. I can't actually remember this the question, but know that term. Okay, so your job now is to use the same scheme and draw the Lewis dot diagram for magnesium oxide, which is MgO. MgO. So tell me how many valence electrons magnesium has. 2. How many does oxygen have? 6, okay? I don't know what else terms about. Magnesium gets 2 dots, okay? Plus oxygen, which gets 6, right? So you're drawing the valences. And it doesn't necessarily matter. I always draw them in pairs. So you can draw them however you wish. This is probably best, though, just to be honest. Okay, so what do you do now? So magnesium is doing what with this, though? Okay, so it's transferring them. So that's the showing of the transfer when you show an arrow. And then what does it make magnesium have overall at the end? A +2 charge because it lost the 2 electrons, and oxygen to have octet, but what's its charge? A -2, right? Because remember you gain a negative, 2 negatives. And so that, you can see +2 and -2 would be electrically neutral again. How are you doing so far? Easy so far? What are you embedded within pictures? Okay, so I love drawing these things. It's so easy if you know how to do it. Oh, sorry. Fun fact. How does this relate to the trends? Electronegativity trend. Where does how does electronegativity trend? Use your fingers. Right? Up and to the right. So how does this relate to that? Evan, what you got? How does that relate to this? Well, who's more electronegative, magnesium or oxygen? Lies. Right? So magnesium is way over here, and oxygen is way over here. So the electronegativity trend should say that oxygen is the more electronegative. So in a situation where it has to decide who gets the electrons, oxygen's totally going to get those electrons. Magnesium's going to get them because it doesn't want them anyway. So you should be able to relate that back. Okay, so what kind of bond is this? Covalent. Do you see the transfer of electrons? No, you do not see the transfer of electrons. There is no arrow between this one goes over here, this one goes over here. Instead, they just smoosh together, and this becomes a shared bond, as you can see denoted here. Draw this for yourself. This one you commonly see in a slightly different manner as well. You'll see chlorine as a single bond, so that, just a line bonded to another chlorine like that, instead of the two dots in the middle. But the two dots are equally acceptable. This is just easier to draw. And then you still have to put those lone pairs. These are called lone pairs of electrons on the outside because they still have to show that there's octet around that chlorine. So here's how the octet works in this case. I'm going to circle some stuff up here, okay? So this chlorine that I'm circling in red right here has 2, 4, 6, 8, because it's pretending that it's owning those, but we know it's sharing. There's 8 there. And then the other one equally has 8. 2, 4, 6, and then 8 in that shared location. Despite the fact that they're sharing, they still call it their own for that octet rule. Okay? So this one relates because why is chlorine not going to give up an electron to the other chlorine? So they're the same element, so they're equally electronegative, right. So they're equally electronegative. So that means they're not, neither one of them is going to give up the electron. They have to share. It's just how the rules work. So what do you think about hydrogen? Look and find hydrogen. And then chlorine. What do you think they're going to do? Do you think they're going to share? Or do you think they're going to try to donate? Or do you think that they're just not going to share equally? Look where they are. We got hydrogen way over here, chlorine way over here. And so we're making some, what are our predictions? So we're feeling ionic right now, right? Let me help you out. This is called an electronegativity chart. Do not steal these. I will find you. I don't want you down. And then it's just names on, okay? So take a picture if you want. These are approximately the same as the yellow ones and the white ones. The white ones are actually better. The yellow ones are slightly skewed because somebody else put these in. They didn't double check values. So pass that piece. I think there's another. Pass those values. Okay, so look at your electronics. Is there one more? Some of these are like the last leg. This one's looking okay. Anybody else even? Okay, so find hydrogen and find chlorine. I want you to tell me the numbers that are associated with them, the electronegativity numbers that are associated with them. So hydrogen, on the yellow sheet's at 2.2, on the white sheet's at 2.1. I'm just writing 2.1, that's close. On the chlorine, 3.0 or 3.1. Okay, so what's the difference in electronegativity between these? Actual mathematical difference. 0.9, so the change is 0.9. Okay, look at 0.9 on the little chart down towards the bottom where it says polar covalent, non-polar covalent, and ionic. Do you see that? Where does it fall? 0.9? 0.9 falls in the polar covalent. Okay, we're good? It's in the polar covalent region. Okay, so what does, according to reading guide 8, what does polar covalent mean? That's why I've left these on your desk for now. Or what does non-polarity mean? Okay, hold on. Hayden, Kayla. Polar is where the electrons are. Okay, polar is where electrons are unequally shared. So basically what that means is there is a bond here, guys. It's a covalent bond. It's hydrogen, and I'm going to draw a long bond here, just for explicit, showing you where the electrons are. Bonded to chlorine, right? Normally electrons exist equally on this bond. This bond is actually representing 2 electrons, okay? Normally it's like, all right, I'll stay on this half, you'll stay on this half. That's equal sharing. So what would unequal sharing look like? So maybe they're closer to one or the other. Who do you think they're going to be closer to? Why chlorine? it has a higher electronegativity value. Electronegativity refers to the greediness of the atom for a bonded pair of electrons. So instead of drawing, so I want you to write this down for yourself so you have a picture with it, okay? The electrons, they live in the bond between them. The internuclear axis is what it's called. But the electrons are not staying close to hydrogen at all. They're going to kind of just shift their little bodies towards chlorine side, but not be donated, not be ionic. They're just hanging out with chlorine, I don't know, 6 days out of the week versus the, 1 for hydrogen. They're still sharing it, just not equally. So that's called unequal sharing, which we call a polar covalent bond. Unequal sharing is a polar covalent bond. So this is one of the more conceptually difficult things because that polar part, you gotta know that means unequal sharing. And how does it look? The electrons are on one side. There's another way to draw it though. We draw something called a dipole moment, okay? Dipole moment. Above the bond. So which of these is more electronegative? Chlorine. Okay, so you draw an arrow towards chlorine, and then you put a little hash mark on the hydrogen side. So which way am I pointing towards? The more electronegative or the less electronegative? The more electronegative. Okay, so the dipole moment points towards the more electronegative atom. And the hash mark, it looks kind of like a plus, doesn't it? Doesn't that kind of look like a plus? Yeah? It's on the less electronegative, so the less negative side of the bond. Okay? So I'm telling you some stuff up front because I'm not going to spend a lot of time on it later. This is something that we're going to use a lot today. Okay, so what do you think? If the chlorine side has more electrons around it, do you think it's partially negative or partially positive? If it's got more electrons around it. Partially negative, probably, right? And so sometimes we'll actually depict that with this little things called a sigma. It's a lowercase sigma and a negative. It's like a little, almost, it's like a lazy 8. You didn't quite finish the 8, and then a negative. That's called partially negative. And guess what this side is, guys? Partially positive. So you'll see this little half 8 thing to indicate the partial negative or the partial positive nature of that end of the bond. So this is just called partial positive, and that one's partial negative. Okay, so those of you writing down everything I'm writing, you're going to be in good shape. If you're just observing it, I hope it's sinking in. Okay, so look at, let's do a couple more of these. This is exactly what I just said. Give me an example of something with a nonpolar covalent bond, meaning the electronegativity difference is in that nonpolar category. Give me 2 atoms with a small difference in their EN values. Maybe Paige and Morgan, you guys give me those 2. Ooh, sorry. Let me backtrack. Stick to we're actually off of ionic now. Stick to the upper right hand corner because that's where our covalent bonds will form with nonmetal nonmetals. So give me 2 nonmetals. Carbon and nitrogen. What are the values? I know, ooh, right? 2.5 and 3.0. Where does that fall? That's in the polar covalent region, right? All right. Boron and silicon. Okay. So B and Si. So that's a 2.0 on my paper. Yours is probably close. And a 1.8, 1.9. Okay. But still, it's a relatively small difference. What's the difference here? A 0.1 or 0.2, right? So in this example that I've written up here, 0.1. And that falls in the non-polar covalent region of the electronegativity difference, this continuum we're talking about. So another one might be oxygen and chlorine, right? Look at oxygen and chlorine. What are their values? 3.0 and? What's chlorine for you guys? 3.0 or 3.1? 3.1 or 3.0. Either way, it's still going to be a very small difference. So that would be, again, a situation where we have no difference. Okay, so I am not going to draw a dipole moment on these because they don't have polar regions, so we do not draw a dipole moment. So the one where we do draw a dipole moment, let's go, Nicole, tell me something. You and Jasmine pick out 2 that would create a polar covalent bond, according to the values on the paper. Something with a mediocre EN value difference. Oxygen and... Oh, so oxygen's a 3.5? Oh, yeah. Did I just say oxygen? I couldn't read. Mine is really hard to see. That is a 3.5, by the way. Or did I say carbon up here? What did I just say? Oxygen? Okay, sorry. How about we do, what did we, nitrogen, make this nitrogen and oxygen, and chlorine. I don't want to mislead you. Oxygen's a 3.5. I just can't see that very well. Okay, so oxygen, what did you want to say? And chlorine. Okay, so on your paper it says 3.0 for oxygen. Nope, sorry, 3.5 for oxygen. And a 3.0 for chlorine, yeah? On your paper? So everybody else is pretty close. So that difference is 0.5, which is the interval that's between non-polar and ionic. So we're in good shape here. So what do I draw a dipole moment here? Yeah, pointing towards who? Towards oxygen, right? Pointing towards oxygen, hash mark on chlorine. Okay, so give me something that's ionic. Matt. Not you, Matt. Something ionic. So fluorine, the most electronegative, and boron. Okay. Actually, let's go. Can we go back to just really confirm? Remember, ionics are between what and what? Metals and nonmetals, right? So chlorines are nonmetals. Pick a true metal. Aluminum. There we go. Aluminum fluoride, so that is, right? And you can see the difference here is a 1.5 and a 4.0, and that's a huge difference. So that electronegativity value difference is a 2.5, which is in the ionic region. So you can use this a lot to help you figure out the types of bonds we're forming, right? Okay, so let's actually start to draw some of these. So the ones we're really going to be, so we've already drawn the ionic ones, they're pretty easy. These and the polar covalent, non-polar covalent ones are going to be bigger images. So these are going to be things like, we just did that. We're good here. I'll come back to this. These are some pictures that help you guys see this. Let me start drawing and then I'll tell you what's going on, okay? So let's write down NH3. This one you guys got to draw these, okay? You have a lab on this tomorrow. You'll start drawing them from the lab perspective to build them in these nice, like, these are like chemistry Legos. Yeah? We're gonna play with these. But you gotta learn how to draw them before you can build them. Okay. So NH3 is our example. I'm going to show you how to draw these things in a step-by-step manner. And the step-by-step manner, the acronym that helps you remember it is VESPER. Right here, VESPER. V, number of valence electrons. So write this little step-by-step thing out here to decide for yourself. V, valence electrons. So we actually, let's start with the first step. How many valence electrons are summative when all of these atoms get together? Well, how many does nitrogen have? Look at your periodic table. Just work with me on the V part right now, okay? Stop writing the rest of them. Work with the V. How many does nitrogen have? Nitrogen has 5. Okay? How many does each hydrogen carry? 1. How are we knowing these things, guys? Looking at the group numbers, okay? So you're looking at the group numbers. So each of the hydrogens, there's 3 of them, and they carry 1 each, right? So total that, what's up? 8 valence electrons. Okay. In this entire molecule we're going to draw, we can only have 8 valence electrons. That means 8 dots or 8 little bonds like that, depending, they can only equal 8. Okay, so check, we've done the first one. The second step is to do a skeleton. So the skeleton steps are choose a central atom, then add rest, or add the rest, and a symmetrical pattern. And I actually have a full list. I just skipped it so I can do an example first. And I will put that on the worksheet in a second. But I want you to work through the example in kind of verbal terms before you start looking at the massless constructions. So, who would you think would be my central atom? Probably nitrogen, because the hydrogens are going to equally go around them. Because nitrogen is the best central because it's a singleton. Meaning you can write it in the middle and then write the hydrogens symmetrically around it. Okay? What do each of these dashes mean? How many electrons? 2 electrons. 1 dash means 2 electrons. So there's 2, there's 4, there's 8. I'm almost done. I mean, sorry, 2, 4, 6. I'm almost done. How many more electrons do I have for my total? 2 more to go, okay? So, third step, add electrons to make octet. But there's that one exception. What's that one exception to octet? Say it again? Duet rule, right? Who's so small they can only handle 2 electrons? Helium and one back from it? Hydrogen, right? So look, guys, hydrogen is as happy as can be. It has 2 electrons around it. It's good. It has 2 electrons around it. It's good. It's got 2 electrons around it. It's good. How about nitrogen? How many does it have around it? 6. So it needs 8, right? Octet. So this is where we add something called a lone pair. Just like that. So I'm going to adjust this. I just said add electrons until octet. And then this is where I'll say lone pair, because we might need to, and in this case we had to. Okay, so sometimes you actually have to maneuver these things around and play with them until you get to them to the right structure, and I'll go through that in a second. And that's what this one does. P says make pairs. Like, do we need to add any more pairs, take pairs away, rearrange some of these? We're actually happy as can be. We got octet and we got duet. We're in good shape. The last step is review it. What I mean by that is by review it by making sure you only have 8 valence electrons. Do we only have 8? Yes. Okay. So here's actually what that one looks like. Looks like this. Okay. So I've drawn it here, kind of like a straight T with 2 dots on top. But what's happening is these guys up here, these are 2 negative values, right? These negatives, they do not like these negatives. Because negatives and negatives repel, right? Okay, so they're like bullies, and they push them away. They repel them, okay? And then when they repel so much, instead of having a straight structure, pretend my head is this lone pair up here, these lone pairs of electrons, these negatives repel these negatives, so it pushes it down. And when it pushes it down, it changes it from a 2D shape to a 3D shape. Do you kind of see that's a pyramid? Okay, that actually has a name to it. Turn on the back of your sheet, your little electronegativity sheet, and I want to show you how you figure out the names of the geometries, the names of the shapes. What we have here is the central atom is nitrogen, okay? What's the first column say for you guys? Say again? Ligands, okay. So the number of ligands are the number of legs attached to the central atom. So ligands are like attachments of atoms, not of lone pairs, of atoms. So how many atoms are attached to nitrogen? 3. 1, 2, 3. So 3 hydrogens. So it has 3 ligands. How many, and you're only focusing on the central atom. How many lone pairs does the central atom have? Just 1, and that's that lone pair up there that's being repulsive. Okay, so 1 lone pair. What shape is that? Trigonal pyramidal. Trigonal, pyramidal. Okay, that is basically everything we're doing from here on out. We have one more kind of concept to talk about, but we're going to do that a lot. Okay, draw it, look at it, determine its shape by looking at the thing on the back of your paper. Okay, so here are the for real instructions. Don't be scared. Hold on. That's everything. Read it, write down what you need to, and then we're going to do a couple more examples. And while you're reading it, write down what you need to, and take a break, walk down. I have a couple more for you. There's a couple of additional details that will be helpful. So you're totaling valence, that's our V. Choosing a central, which is our skeleton. There are some adjustments to that. The carbon is generally in love with other atoms, so it likes to bond 4 times. Great bonder, loves to be in the middle of attention. Singleton or largest, what's up? Yeah, carbon for C for carbon. So that's our skeleton. And then E, give everybody octet or duet, if hydrogen doesn't already have it. And sometimes you have to add lone pairs. Sometimes you have to redistribute some of the lone pairs. And I'm going to do one of those for you you this more complex version of this. So this is the one part that I didn't say yet. It's kind of our P for pairs there, okay? If you have an extra electron added to the central atom, that is going to come into play when we get into more of the complex one. Sometimes you're like, everybody's got octet, but I've got more electrons, what do I do? Then there are some things that can expand octet. They're special exceptions to octet. Basically, I don't know why we call the octet rule. It's not really a rule. It's kind of like a thing that happens, and everything else does the same thing. You do it or octet. And then we're going to try some with single and triple bonds. Let's usually take a break for a minute. Get walk around. Put your little baggies back together. Go see your Mythbusters friend. You got one. Are you making your Chem Club meeting today? Chem Club? CLB? All right, great, guys. Thanks for support. I understand you probably have something better to do. Okay. So, next one. For you guys, carbon tetrachloride, CCl4. Go through your process. I want to see what you can do without me first. CCl4. Your very first step. Counting, yes. How many valence electrons do you guys have? 32. 4 from carbon plus 28 total from the 4 chlorines with 7 valence electrons each. Okay. What was your next choice? What was your next choice? Find the central, which would be who? Carbon, and then bottom up. How many bonds have I used simply with the skeleton? I mean, how many electrons have I used simply with the skeleton? 8, okay? And then how many have I used now? 32. And I like to count by 8s because I never get time to count all those. There are 8, 16, 24, 32. So you don't have to draw the little loops around them, but that's what it looks like, right? There are 32 because I'm counting 8 around all of the chlorine, including that bonded pair there. So there's a lot of lone pairs, but are they on the central atom? No. So look in the back of your sheet. How many ligands? 4 ligands, which are the legs, the attachments of the atoms, and how many lone pair on the central atom? 0 lone pair. What's the shape? Tetra. What does tetra do you think it means? Matt, what's it mean? 4, right? Who's a tetrapod? Okay, no, we are what kind of pods? We're bipods. We're bipedal. We have 2 feet. Yes? Animals, other animals are tetrapods. Yeah? Okay. Biology. Okay. Tetrahedral means 4. Okay. So that one looks like this. Okay? You see it? Can you tell that angle right there? you guess what it is? Is it a 90-degree angle? No, it's not. It's actually 109.5. Write down this for me. 109.5 degrees. It is not a 90-degree angle. So what I can do is I can turn it every which way. Every single angle is exactly the same because it is symmetrical in the 3D pattern. Because 90 degrees would only be symmetrical in a 2D pattern, like this. That's what it looks like here because I can draw 3D. Here's what it looks like 3D. You do this a lot in organic chemistry and in AP chemistry. These are in a 2D plane. This one's going back, and this one's coming forward. Kind of what it's supposed to look like. I'm not this. Okay, so that's what it looks like. We're gonna build these though, so I think it'll make more sense. So far, so good. Yeah. Let's do a harder one. Let's do nitrogen. 71% of our atoms, right? Nitrogen. What's your first step? Count them. How many you got? Right, because you just feel so quiet. Nitrogen carries 5 valence electrons each. So how many total? 10, because there are 2 of them. Okay, who's a central? We don't have a central, really. Like, what do we have to connect, guys? Nitrogen connects to, guess what? Nitrogen. There's no options here. You can't get this wrong. But go ahead and give everybody octet. Sorry. Let me make my dots really big and beautiful here. There we go. How many valence electrons do I have here? Or how many electrons do I have on my model? 14. So I've got way too many, right? So 2, 4, 6, 8, 10, 12, 14. So what I have to do is I realize that I need to get down to 10, right? So I have to start making them share more. How do I make them share? Do what? How do I move them to the middle? What kind of bond am I making? Currently I'm at a single bond, so then what would I be making? A double bond. And if I have to make them share again, I make a triple bond. Okay, max out a triple. There's no such thing as a quadruple bond. All right, so what you do is you erase 2, so 1 lone pair from one and 1 lone pair from the other. And you're like, all right, guys, you're going to have to share. We put it smack dab in the middle. How's that solve my problem? Count them again. How many do I have? 2, 4, 6, 8, 10, 12. Okay, so what do I need to do again? Yeah, you're like, all right, guys, no free electrons for you. That lone pair goes away, and the second one on the other one goes away. And instead of making them have that separate lone pairs, you make them share again. So now we have a triple bond. That's what I mean by review it and adjust it. So at the end, we're like, oh, now we got 14. We need to adjust it. That's what I mean right there, okay? So we have a triple bond. We don't have a central, so that back sheet's useless to us, right? What kind of shape, looking at the shapes though, what kind of shape do you think that is? Nitrogen, nitrogen. Say again? What's it called on the back of your sheet? Linear, right? There's only one way you can connect 2 dots, and it's through a line, so we call it a linear geometry, a linear shape. So that one doesn't have a cheat sheet, but it makes sense. Okay, let me stop for a second, and you guys have this lovely lab tomorrow. So what I'm going to have you guys do is draw the electron dot structure and determine the bond polarity. What were our options for bond polarity again? Non-polar covalent, polar covalent, and ionic. Oh, sorry. So you're going to have to do that for, take a picture of your little sheet if you want to. I'll see a sheet. I'm having my bundles of them extras just on the back lab. So I'll do the first example with you, and then you're going to start, okay? Everybody have a sheet? Okay, so we're going to start with CH3Cl. We're going to do the bond polarity and the electron dot structure. If you cannot put it on here, you put it at the back of your sheet to work with. I'll tell you which ones I want you guys to do the electron dot structure for. We have about 10 minutes in class. We'll probably knock out a couple of these now. But for CH3Cl, let's draw the structure first and then go back to the bond polarity, okay? So, structure me up. What's the first one? First step. Count them out. Okay, how many does carbon have? 4 plus how many from each hydrogen? So 1 from each, so that's a total of 7 thus far, plus chlorines, which is 7, so total 14. 14 valence electrons. Write that up to the side so you don't forget we just counted because nobody wants to count again. All right, who would be my center? Carbon loves them bonds, okay? He wants to be in the middle. So then what do you do with the rest of them? Bond, 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 bond. Hydrogen, and just make them as symmetrical as possible. I mean, you can't really... You guys finish it. We lost. Okay. 3 hydrogens and a chlorine. Okie dokie. Now what do? The dots around who? Why chlorine and not hydrogen? Okay, so it's already maxed out at duet, right? So hydrogens are happy as can be. They're at duet. Chlorine needed octet, so chlorine's happy now. So we have around chlorine 2, 4, 6, 8. Carbon 2, 4, 6, 8, and each of the hydrogens have 2. All good. How many valence electrons total in this structure? Hopefully 14, right? So 2, 4, 6, 8, 10, 12, 14. Yes, score. Okay, so we have 14. Now, look at the bonds that are present here. So we've got the structure drawn, right? We're good with that. The 2 bonds that are present are carbon bonded to hydrogen, okay, and then carbon bonded to chlorine. Are there any other bonds present? Nay. Okay, so that's what we have to do for the bond electronegativity. What's carbon's number on your sheet? 2.5. Okay, what's hydrogen's? 2.2 or 2.1 on the other people's, I think. So regardless, what is our difference here? I'm going to write it as a 2. Well, carbon to hydrogen's 2.1. Well, that's actually a little different on both y'all's. I'm gonna show it both ways. I'm gonna go with the 2.1 because this is the one that I've always used. I halfway got this thing memorized. So this difference is 0.4, which for some people says polar covalent. If you're the 2.2 person, it's non-polar covalent. But that's what I want you to do. Whichever sheet you have will work. I just want to make sure we're good with the process first, then we'll get into the details. So if you're a 2.5 and 2.2 person, the difference is 0.3. That's non-polar covalent difference. How about the other one? This is a 2.5 and a 3 point for chlorine? 3.0. Oh, okay, so 3.0. Sorry, I was thinking 3.5. So what's that difference? 0.5, so what do we call it? Polar covalent. All right, PC is fine for me. NPC is fine for me. Help you a little bit on your abbreviations. Okay, so I want you to do those 2 columns for, actually, try them for all of them. Because tomorrow we'll fix them tomorrow. I want you to try them for all of them. So there are 12 structures with their bond polarities. Okay? So slow down for me. Yeah, we've already drawn, I think, 2 or 3 of them.
to do that, right? Agreed. That is 7 electrons. That's 2, 4, 9, 1, 2, 3, 4, 5, 6, 7. Wait, so I have to go. So I always. I don't know. And then. Oh, because those are the main. The outside. The outside's almost going to happen. Yeah.
So guys, if you get stuck, I really want you to keep pushing through because there's some of them are actually going to not fall exactly as we did today, all exceptions. But we'll talk about more tomorrow. So I'll just try. Yeah, we we do get out in just a couple minutes. If you have not been to unit, while you're packing your stuff up, okay? If you've not been to unit 3, reading guide, I will take that tomorrow because you guys might need it for your like the descriptions. Okay. All right, guys. At the very bottom of unit 3, it says electronegativity's geometry chart. That's the one. That's the better one. The yellow one has some questionable numbers or no numbers. Okay, that's the better one. But bring questions tomorrow. Reading guide that I'm taking tomorrow. You might need it for some of your terminology that when we were reading last. Okay. Peace. I'll see you tomorrow. And we'll keep making a deal. Chem clubs. CLB. I have AP Chem. I'm tutoring, but you can say more. That's fine. If you're chilling in here, do your stuff. Do what you gotta do. Oh, sorry. So, this review, but basically what we're doing tomorrow is we're going over a couple more notes on stuff we didn't finish today, and we are building these structures. Okay. So tomorrow,
I just wanted to make sure.
yeah, and I tried to make it as easy as this is you to come back and build these with me, our partner, and then finish these structures. Really just finish this one tomorrow. That'll be very helpful. So help you fill the rest of the chart. Okay. Thanks, Nicole. Yeah, well, it's gonna be a lot of people in here. You can try, but oh, 4 Chem Club, yeah, but there are gonna be a bunch of people in here. So if you're coming here just to chill, it's probably not a good chill time.